Hey there, everybody. Welcome back. We're going to start 13.8 in our Calculus 3 class. This is on finding maxima and minima for multivariable functions. We're using Anton 11th edition. This is Calculus 3 at Colleges of Sequoias in fall 2022. Let's just jump right into it. Let's think back to what we did when we had single variable functions, y equals f of x. To find the maxima and minima, we had to find some critical points. And we could find either local max and mins or an absolute max and min. The absolute local would be it's the max or min in a small region, absolutes over the entire domain. This is definitely possible when we shift to multi-dimensions. Like picture the Sierra Nevada, or just mountains like I would say right here might be the absolute max, but we can find a local max right here. We can find local mins all over the place and little local maxes too. So this is definitely doable. Let's just take a look at how we go about doing it. And we found critical points, and we found we used the second derivative to test things. We're going to do that here. So let's just get some definitions and theorems out of the way in this first video. F of xy has a local maximum at x naught, y naught. If there is a disk that's centered around x naught, y naught, such that that value, the function at x naught, y naught, is greater than f of xy for all the points inside the disk, and that makes it a local maximum. And then it's an absolute max if it's actually true on the entire domain. We want to switch this to minima. All we got to do is change the word from maximum to minimum and just change the inequality to say less than or equal to in both these cases. So we'll have some disk, and there's a point in the center, and everything around it, the point in the center has a greater value than everything in that disk around it. Okay. Local maxima and minima are collectively called the local and relative extrema. Singular version is extremum. And then we got the absolute max and min are called absolute extremum. Okay. Let's continue on. So to go forward, we got to define a couple more things. Sets and regions that can be entirely closed in a rectangular box are bounded sets. And if a set of points cannot be entirely enclosed, we say it's unbounded. So if f of xy is continuous on a closed and bounded set R, it has both an absolute max and an absolute minimum somewhere in there. If f has a local extremum at x naught, y naught, and the first order partial derivatives exist, then the first order partial derivatives equals 0, which makes sense. We need it to be a peak or a minimum. And we need that slope there to be 0 in both directions. And that's similar to what we did with critical points when f prime of x was equal 0, like, you know, the max or the min, the slope was 0. Critical points were also where f of x was not differentiable. So like the function 1 over x, it should say 1 over x, is not differentiable at x equals 0. It's a critical value to take a look at what's going on. And finally, a point x naught, y naught in the domain of f of xy is called a critical point if the two partial derivatives equal 0, or either one of them doesn't exist. So we've got something going on there. Generally, if one doesn't exist, the other doesn't, but not necessarily. And that's it for the first video. Peace.